Hello and welcome to my Viva, where I shall present an investigation into complementary control of multimodal transistors. My name is James Mutumba and I've worked on this project with supervision from Dr. Radu. Here, I present an overview of this presentation, beginning with the motivation and objectives behind this project, followed by the background theory of associated devices, our methodology, research results and their discussions, conclusions, and the basis for future work, and finally, project management. The motivation for this project comes from the fact that biological systems far outperform digital implementations in adaptive computations and those that require learning and development. For decades, there's been a rising interest in artificial neural systems that mimic brain functionality. Two of the fundamental aspects of brain neuron functionality are inhibition and excitation. Neuromorphic systems aim to mimic neuron functionality using physical artificial neurons made from transistors or memristors. The MMT, with a different control methodology from conventional thin film transistors, offers an opportunity for complementary control for positive inhibition and excitation, from which this project draws inspiration. To achieve the aims of this project, several objectives had to be set out. To understand device physics and structure, thorough background research into thin film transistors was required. This also encompassed the incremental but advanced systems like the source-gated transistor and the multimodal transistor, which is ultimately under investigation. Since this project was entirely simulation-based, a grounding of the simulator used was required to allow for modeling of parameterized and configurable devices starting from the TFT all the way up to the MMT. After creating an MMT device with the behavior described in the available literature, the last objective was to develop an MMT structure which incorporates either a backgate or a heterojunction structure with implications to the drain current leading to complementary control. For complementary control to be achieved, the transistor turns on after a threshold voltage is reached and should grow linearly as expected of multimodal transistors. This would be the excitation stage. Current should then saturate at some voltage value, after which further increases in voltage would then lead to current decay, which is the inhibition stage. We begin our discussion with the base device, a thin film transistor. Structurally, it is made up of a thin active semiconductor layer and dielectric deposited over a sizable inexpensive substrate like glass or plastic. Source and drain electrodes are joined by a semiconductor layer, and a gate electrode is separated by an insulating dielectric from the source and drain. Thin-film transistors find significant use in large area electronics, and hence their active layers are usually fabricated using low-cost materials like amorphous silicon and polysilicon. These devices operate as field-effect transistors, where a gate electrode modulates the conductance of a channel and current saturates when the drain end is depleted of carriers, a phenomenon known as pinch-off. TFTs, however, have several issues, like poor saturation characteristics, where the drain current continues to grow after saturation. This exhibits short channel effects with reduced channel length. Drain-induced barrier lowering also occurs where unintended source-drain interactions lead to punch-through current leakage and loss of gate control. Because of the aforementioned issues, the source-gated transistor provides improvements to the thin-film transistor by addressing some of the issues of the TFT. An SGT has a deliberately introduced source barrier with a gate located directly above or below the source. The gate controls the source barrier height using the field effect. A slight positive drain bias will then reverse bias the source barrier, and a current will flow over the source barrier to the drain end. When drain voltage increases, the depletion layer under the source barrier begins to extend to the semiconductor insulator layer, saturating the current and hence fixing the source barrier electric field to the gate voltage. This isolates it from further drain voltage increases, hence pinch-off starts to occur at the source end as shown. Further increases in drain voltage eventually show a second pinch-off at the drain end. Due to the above described characteristics, the SGT hence shows improved characteristics like lower saturation voltage. Due to the source barrier controlling the current, a gap between the source and the drain has little influence on the current magnitude. Hence, electrical characteristics will remain primarily unchanged even when the drain-source separation is not uniform. Work for this project has been carried out entirely through device simulations using Silvaco TCAD. The initial structure modeled was a TFT from which the SGT and the MMT were born. These structures were parameterized to make them easily configurable to allow more advanced devices like the backgated MMT and the heterojunction MMT to be modeled quickly. One of the critical modeling techniques in Silvaco is the definition of a mesh. A mesh covers the physical simulation domain. The specification of meshes involves a trade-off between the requirements of accuracy and numerical efficiency. This was crucial especially for the heterojunction MMT, where I faced several convergence issues due to the bulk and junction meshing parameters. Definition of a well-structured mesh allowed me to arrive at convergence in a reasonable time. Silvaco TCAD, a physical-based simulator, requires definition of physical models, which allow for simulation of the transport of carriers pertaining to the defined structures. Some of these models include MOSFET models and Fermi statistical models. After modeling and simulating the TFT and the SGT, work on the MMT, which was the main device for the project, began. The MMT was modeled using the previously configurable SGT with a similar source barrier. The gate, however, was separated into two control gates, which were control gate 1, which controlled the current level, and control gate 2, which halted all permitted current flow. For purposes of this project, and due to the drain-induced barrier lowering issues which were described earlier, the MMT device was modeled with a field relief plate in the source region. The control strategy currently of the MMT is such that when a positive voltage of CG1 is applied, electrons accumulate at the semiconductor insulator layer under the source. Without CG2 voltage, however, there is no charge transport, as a resistive channel would exist across the source drain gap and the device would still be essentially off. A positive voltage on CG2 without CG1 would lower the resistance in the channel, but no current would still flow. Applying a simultaneous positive voltage on both CG1 and CG2 and a drain bias would allow for charge injection and transport, and hence charge would flow from the source to the drain. To turn the device on, a positive voltage is thus required for both CG1 and CG2, and to turn it off, a negative voltage or zero voltage is required. The transfer characteristics shown here in this graph assert this. Since both the SGT and the MMT were born out of source area engineering, it's only logical for this project to focus on investigations of changes in this area. One of the ideas for complementary control was the addition of a backgate in the source area, which opposes CG1. The rationale was separating the source electrode and field plate to create a backgate would inhibit charge injection as CG1 enhances it. The idea was to turn on the device using a positive CG1 voltage and turn it off using a positive backgate voltage, which would inhibit drain current. Additionally, experimentation with the semiconductor region in the source region would also directly impact the device's current level by using compound materials. The idea of this was to create an abrupt NN heterojunction in the source area using lattice-matched materials like silicon and germanium, which have well understood junction parameters. NN heterojunctions are isotropic and hence have majority electron carriers. The barrier to current flow is thus in the conduction band, which is determined by electron affinity difference of the two semiconductors and by the doping levels of the materials at the junction. It was predicted that these band discontinuities on forward bias would result in band bending, which would affect the current injection process at high CG1 voltages, reducing drain current and eventually turning the transistor off. Both the back gate and the heterojunction MMT were modeled, and their simulation results are discussed below. Simulations were run for CG1 transfer characteristics of the backgated MMT device at different backgate voltages, and the effect on its drain current was investigated. It was observed that drain current increases when a backgate voltage is applied, instead of the intended result of drain current decay. Electron concentration cut lines in this structure reveal that backgate accumulates a semiconductor layer below it, creating a second channel in the device similar to double-gated MOSFETs. The backgate additionally shares control of current injection with CG1. As a channel is accumulated and drain current flows even when CG1 is off. This would not be useful, as it would contradict the need for CG1, and it would degrade the MMT's functionality. The device was thus discarded, as it showed a deviation in the behavior that was required. The second device that was simulated was the heterojunction structure, and the affinity of the material contacting the source electrode was varied to investigate the effect of conduction band offsets and discontinuities on the drain current. When this was done, the work function of the source electrode was also varied to ensure that there is a constant source barrier to not taint the results. At equilibrium, silicon is at a higher conduction band energy, and the bands bend downwards to a lower conduction band energy of germanium. When the junction is forward biased, the conduction bands would then bend downwards, hence there is a steeper band bending for increased conduction band offsets. Heterojunctions in MMT also have the effect of drain current saturation with CG1 in contrast to a regular MMT. This was an important discovery. This is because a silicon germanium NN heterojunction creates a dense set of interface states near or below the center of the silicon band gap. This has the consequence of creating double depletion layers on both sides of the heterojunction. The device thus shows double saturation for both positive and negative voltages of CG1. The magnitude of drain current injected by CG1 increased with reduced conduction band offset, which asserted the simulation prediction that increased conduction band discontinuities would reduce the amount of current injected by CG1, leading us, which is a step towards complementary control. When the doping was increased, the drain current increased and the saturation voltage of CG1 was reduced. This was in line with the expectation that increasing the doping of silicon would move the conduction band energy down, reducing the offset between silicon and germanium band offsets. Electrons can be easily accelerated into the conduction band of germanium from silicon by application of a bias on CG1. In conclusion, a host of devices were explored in this project, starting from the TFT to the more advanced heterojunction MMT. The heterojunction MMT showed some effect on current reduction by low drain current saturation with CG1 voltage, which forms part of the solution towards complementary control. A combination of conduction band offset and doping was showed to influence the current level at which this saturation occurs. However, no suitable device iteration yielded drain current decay with increased CG1 voltage. Nevertheless, the research contained here forms part of a more extensive investigation, and further work into this could reveal exciting implications for current control, and I would like to think the project was primarily successful in providing grounds for this. Future work based on this project will focus on other materials like 3 to 5 compound semiconductors, which are more understood and are under a more extensive technological control for purposes of fabrication. Floating gate architectures could also be considered. To keep track of the project and ensure delivery is on track, several tools were used in its planning and organization. 2 Gantt charts were prepared, splitting tasks into manageable chunks with reasonable timelines, dependencies, and milestones. Throughout the project, 5 different devices, each with different iterations, were created. These devices had multiple files, and it was crucial to ensure they were named and organized accordingly. These were stored using OneDrive, and revision control was also used to allow ease of access to roll back to last known working device versions. The project relied on collaboration with the supervisor and other team members working on the MMT. This was achieved through communication channels like Slack and in-person meetings to discuss project progress and brainstorm ideas. A risk assessment was also drawn up to ensure that eventualities were also catered for. One of the challenges in this project was availability of the simulator, and these eventualities were catered for by making a risk assessment plan. Thank you so much for listening to me.